All right, we've got our rewrite implemented, and I think we're ready to implement some compressed sensing. A project like this can go on forever. Like I have so many ideas of things that could be done to it. It's already taking so much time. It's been a lot of fun though. Okay, before we get to compressed sensing, I looked through the code a little bit and I found an issue. What's the issue? Let's get to this point where we have a true image just so we have an array of the right size. Okay, ASDF is equal to 0 size image true. Now, let's look at the noise coordinates. That is not where I wanted it. That is where the toes are. Here I'm showing just the real part, I guess. So we're inadvertently putting signal in with our estimate of the noise. That's why the noise bound is so high, and all of that is a problem. So when I loaded the data, I thought I changed this to be the upper right-hand corner rather than the lower right-hand corner, but I must not have saved it in this stuff.mat file. Let's make the sample mask. Oops. Let's make the sample mask. Now let's save these new coordinates in the noise in the stuff.mat file. Great. Now, let's do the same test. Okay. So column all the way on the right. Right, because MATLAB is 1 based, so that should be 256. Let's do it again. Actually, so I guess that should be 193. Yep, 193. Okay. Now I think we finally got some good noise coordinates. Let's do the same test again. Gotta get to image true. There we go. You could use, much more of the data, but that should be enough. Much more of the image. Okay. So now, let's see what the noise bound is. 4 times 10 to the -11th. And you'll recognize that that's between, 1 times 10 to the -8 which was way too high, and 1 times 10 to the negative 12, which was the arbitrary amount. That looks like a good amount to me. I wonder what this image is going to end up looking like with a reasonable noise bound. Okay. That's what it looks like. For better or for worse, with something like 1/6 of the data, that's what it looks like. We haven't checked in the code in a while. Let's do that now. All right. We have got a noise bound, spirit regularization, and a non-rectangular support. Now, I'd like to add in compressed sensing. Noise bound is not here. You know, I write these comments as I go along, but what we'll do is, before we publish this code publicly, we'll take one last look through these codes, through these comments, and make sure they're what we want them to be. Okay. So this is the problem that we're going after. I got to see Ingrid Debichet present one time at the joint math meeting. And it was really beautiful because in the middle of her presentation, she promoted a charity. The charity was supporting PhD students in math in Africa. And because Africa is so impoverished, the cost of getting a PhD there in math is something like 1/10, 1/100th the cost of getting a PhD in math in the US or in Europe. She gave 2 lectures, I think, and maybe 3, and in every lecture, she promoted this charity. I didn't understand a whole lot of what she was talking about, but during her lectures, what I did get is she came up with a new, let's see. She came up with a new sparsifying transformation, not a wavelet transformation. It's going to take forever to find it because she publishes so much. Even she's doing neural networks. Well, I'll have to look for it at some point, but either way, we'll be using psi. Now, an interesting thing is that when psi is orthogonal, as it is in the Debichet 4 wavelet transform, for example, then this function, this entire function, has a simple proximal operator. But when psi is not orthogonal, it does not. So what to do? Well, first things first. I can't find a way to automatically figure out when we're using compressed sensing or not. So it's a parameter. Oh, that's my alarm to wake up for the morning. Okay. Right. Phi psi. Because we're going to allow people to specify a different sparsifying transformation. Another thing is, notice I'm using the L1 norm here. I think it would be much better to use the Huber penalty, which we'll do at some other point. Let's add in a to-do. I don't know if the Huber penalty is a norm or not. Building's shaking. Okay. Right. How do I do this? Okay. Oh, can't do it. That's the best I got. I do not have comments for this function, make wave split. I think it was written in 23. I don't know. Nope, 2019. Also don't have usage. That reminds me. We should check in differences here. This one we should be careful. Okay. Oh, actually fixed a bug there. Soft thresh. I changed something in soft thresh. Usage. Okay. Okay. So what's happening? The wavelet transform, if you have an image that's 256 by 256, the wavelet transform passes a low-pass filter and a high-pass filter in both the horizontal and vertical dimensions, and then downsamples. Okay. So that divides that. So, the upper left-hand corner of the wavelet transform is the low-pass filtered, horizontally low-pass filtered, vertically image. The upper right-hand transform is the low-pass filtered vertically, but the high-pass filtered, the low-pass filtered vertically, but high-pass filtered horizontally image, etc. And then what you may want to do is do the wavelet transform again on the new blocks that resulted from the first wavelet transform. That's what wave split does. Lets you do that. It's funny how look at how significant a warning that is. Other issues don't get highlighted for some reason, but MATLAB really wants us to use a scalar, which presumably is a very small difference in performance. Fine with me. Okay, so now I think we have a default function, the Debouchet-4 wavelet transform, which is what this is. It says Debouchet-2 here because this is doing the two-dimensional Debouchet-4 wavelet transform. This, by the way, should be rewritten. I did this very slowly. Actually, I don't know if it's all that slow, but it only works for images that are of size is equal to 2 to the n for some integer n. 128, 256, 64, 512, etc. So I should rewrite this and this to work with images of arbitrary sizes. I don't think we're going to do that today. Okay, so we've got psi coming in. Let's check its adjoint. Wave split not assigned. Huh? Oh, right. Wait, what? See here? Output argument not assigned. Really? Sure looks like it's assigned. Okay. Apply psi. Oh, right. This would just be psi. Function, unrecognized function or variable. Psi is already a function handle. It passes. Okay. Okay, we have got a sparsifying transformation, the Debouchet 4 wavelet transform. Now what? So here's GDC, which was the objective function here. Or maybe like half of that squared or something. Yeah, half of that squared. But now we want an indicator function for this. Oh, goodness gracious. Okay. This is GDC of x. Well, this is 2 times GDC of x, because GDC of x has that 0.5 in it. So 2 times noise bound GDC indicator. 2 times noise bound. Of course, noise bound is not always supplied, right? Times NB square root. Is that right?
Uh-huh.
No, no square root, just that. Only do that if noise bound is a value. Now, one of these to-do items was to take a different noise bound into account for each coil. So that's going to be a different indicator function for each coil, which we've done for the gamma. Can be done, no big deal, but the more we code without doing that, the more we'll have to change later. This is what we're doing. Okay. There's no A here because that gets embedded into the A matrix for PDHG, which we're going to use to solve this compressed sensing problem. Now we need the proximal operator of that thing. We're going to take noise bound Let's take the square root of this. Oh, okay, yeah. So this this highlighted region is GDC. So I think I made a mistake, didn't I? This should be 0.5. Okay. So this is projection onto a ball. Wouldn't you just know it? Ah, P is the norm. What happens if you don't supply P? And it just sets it to 2. Doesn't matter. I can't make up my mind. Okay. How much of this did I make a mistake on? I'm using GDC here. I don't have to. I could just use norm again. I'm concerned if sometimes X doesn't come in as a column vector, what happens here? I guess I should make sure X is always a column vector when it goes into GDC. Or maybe not, maybe B. But see, if X and B are both matrices, which is conceivable but not likely, I'm thinking B is a column vector. If they're both matrices, then that norm is going to return the matrix norm and not the L2 norm. Is it possible for this to return anything other than a column vector? I don't know. So I'll worry about that later. Okay. Again, the proximal operator is a projection. The proximal operator of an indicator function of an L2 norm, of a norm, is a projection. And so we're not going to, this parameter T doesn't get used. I think this is wrong. So the bound has the 0.5 in it. What happened to the 0.5 here? And with that, I am done trying to use GDC. Okay. Should you be able to use it, right? I mean, it's just a half. I cancel out, I divided by the square root of 0.5 here to get this. I think that's right. Which means that we can do this. We've got the proximal operator. So now we're in for it. Okay. We need all of these options. Well, no, we don't need all of them. We can only use compressed sensing if we're also using, if we also have the noise bound. So I could put inside here if compressed sensing. I could put inside here if compressed sensing. And I could put inside here if compressed sensing. And the only other option is We're not doing either of these, but we are doing compressed sensing. If CS equals true, and use PDHD equals true, so here, apply A is going to equal concat psi with MFS. So now I need a concat psi with that MFS. Where is concat anything? Okay. I need to know inside out. Let's check that. I'm not checking any concatenations? That can't be right. I thought I was. Huh. Thought I was. Still doing checks. Let's see if anything runs. It got to the check, and then it crashed. I think this should be NB in length. Eight, 89368. 89368. I was right. Okay. This should be size image. It is. So is it just because I need a reshape? It is. Oh. Yeah, okay. How does that work? Yep. The check of that thing passes. Why did I put an underscore there? If psi is orthogonal, I'm wondering if I could solve this with Vista. That's what I'm thinking about right now. Psi is in the special case when psi is orthogonal, this has a simple proximal operator. But no, because this also just has a simple proximal operator. Neither is differentiable. Off we go. Where does junk get called? I don't know. If something crashes, then that's where it gets called. Okay. G equals at in G. Oh, Lord. Okay. D. Nope. I don't know what just happened. GDC, no. GDC indicator. Guess we don't need that. Certainly don't need it yet. G psi. GCS. I need a CGCS. Okay. Okay. Did I just do that? Yes. Why didn't it come up? Okay. $432. Oh, that's why it didn't come up, because it was a bug. Okay. Now let's add in compressed sensing. See where it crashes. Unrecognized function or variable bound. If CS is equal to true, and we must supply the noise bound whenever we're doing compressed sensing. So let's check for that. So now this should error out, which it does. I'm going to stop showing this true image. I also want to stop showing the support. Okay. Ooh. Why didn't that error out? There we go. Okay. Okay, so that's model-based reconstruction with compressed sensing and our noise bound, and it's bad, but okay, I have no idea if that's working or not, but I know that we're going to need a different sample mask for compressed sensing. It needs to be variable density and random. So let's at least do that first. Let's find the sample mask. All right. There's our variable density sample mask. Okay, right now, the way I've got these parameters set, the sample mask for compressed sensing is much larger than the sample mask for without it. So let's just see if that works. No, the answer is no. That is definitely not a good sample mask. I mean, not a good sample mask. It's not a good reconstruction. I don't know why I have SPIRiT right in all of these titles. What's the difference between this and that? Noise bound? Support SACR W size noise bound. Support SACR W size noise bound. So this one's already being done. And this is our idea of using it with a better support. Okay, been at this an hour. Just to be sure, the noise bound is that 4 times 10 negative 11. Yep, that's right. Oh, I didn't change the sample mask. I gotta change the samples. Okay. What if I divide the noise bound by 100? Basically make it 0. Oh, there's a bug, there's a bug, there's a bug, there's a bug. Thank goodness. Nope, there's not. There is a bug actually, but where is it? It's here. Is it? I think this needs to be minus b, and then I think this needs to be plus b. Wait a second. Okay, there's clearly a bug because we're not using the proximal operator of the indicator function. Two bugs. Only 5 more to go. This goes real fast. Come on now. This is with a tiny noise bound too. Okay, I believe there's a bug. This is not working. This is not what compressed sensing does. Especially when you make the noise bound too small. As an aside, what happens if the noise bound is 0 and we're doing compressed sensing? Then it just sets into B. Because this is infinity whenever x is not equal to b. Noise bound is equal to 0. If this is 0, r is 0, x norm is going to equal r. No, x norm, so out's going to be 0. Out would be 0, and then we add b. Yeah, so it just projects, it just sets it equal to b. And that's like replacing the collected frequencies with the values that were collected. That's what that does. What is soft? Okay. Now I got to think. Let's just look up the proximal operator of the L1 norm. Let's look up the proximal operator of the L1 norm. This is soft thresh. TF. Yep, soft thresh with parameter T. Okay. Oh, what does the L1 norm do for a complex value? Returns the magnitude. What is weights? Oh, I see. So this needs to be prox L1 complex. That's not the reason this isn't working. But it at least needed to be fixed. Okay, at the moment, I'm a little stuck. I have other codes that do compress sensing. N2 is 154,904 and unit size 154,904. Okay, I wanted to check that. Okay. Is this still outputting infinities? I really wish it didn't do that. How's the size of the ACR going to set? 19. Let's see what's coming out. I have a function called wave show that shows me the wavelet transform. I think that's its parameter. Scale is invalid. Open wave, wave show. Show scale, wave split. Show scale is not defined, okay. Input to wave show is complex, okay. That's the wavelet transform. That is the only part that looks reasonable. I guess maybe this part here. Why is there so much noise here? Why is there so much noise? Let's look at the zero field reconstruction. That's what the zero field reconstruction does. Wait a second. I still hadn't changed the sample mask. Uh-huh. Uh-huh. All right. Uh-huh. Okay. This is not crazy. You see those blocky patterns? You see these blocky patterns? Those are wavelet artifacts. And man, I really hate that. And what happens if I multiply the noise bound times 10? Do the wavelet artifacts reduce? Like this picture looks better than this one. No, the wavelet artifacts do not get reduced. This is blurry, that's severe wavelet artifacts. The idea is that the noise pattern is incoherent. That's why I thought the sample pattern might have been wrong when I saw the last result. Because I saw aliasing of the toes here, and with compressed sensing, you don't get coherent aliasing. Okay, the noise bound is not changing this result. It really, really, really wants to give me those wavelet artifacts. 1d8. What happens if I just do 1d8? The higher I make the noise bound, the less it should do data consistency. And the more, yeah, and the more it should just minimize the, oh. What if I make the noise bound 0? I was going the wrong way. Man. Not sure what to do about that. Okay, so the issue then is that, like, even when I did hard data consistency and I projected, in each iteration, I projected the frequencies that were collected onto the known values, onto the collected values. It still gave me the wavelet artifacts. So that's telling me that there's just not enough data for compressed sensing and parallel imaging. How much data do we have? 30%. That should be enough. I should be able to get something that changes the compressed sensing artifacts. Not set it to 0, not give me the exact same image out. Like that. That is a brilliant result. Okay. This indicates that there's a problem with the way I'm handling the noise bound with compressed sensing. Or just calculating the noise bound. Got noise values, taking the L2 norm of the noise value squared and divided by the number of elements. So this is what the average value of the noise squared at each pixel, either in the Fourier domain or the space domain should be. Okay. The indicator function. That's the one we're doing. Equivalent to that. Which is equivalent to that. Which is equivalent to that. $491. Oh. This concat function I think I know an issue. This concat function turns things into a vector on output. Oh, and then I reshape here. That's a column vector. Okay, going back to the noise bound. Okay, it looks like equivalent square root of GDC of x is less than or equal to square root of that. Or equivalently, that is less than that. So this is the one that gets implemented here. For the proximal operator, what? I think I need a 0.5 here, right? Let's go through this one at a time. This is what we're doing. This is the indicator function we want to implement. We can multiply both sides by 0.5. And I'll take away an MLB at this point too. So that means GDC, which is equal, on the left, this is the indicator we want to do. The bound is 0.5 times noise bound times NB. Okay. Take the square root of both sides. No. The square root of GDC is this. And so the proximal, so this is the function. This we're taking the indicator function of this, right? Like we're indicating whether or not the left-hand side is less than or equal to the right-hand side. The left-hand side is a norm, so its smallest value can be 0, obviously. So this is the radius of the ball that we're going to project on to. Oh. I was thinking X and B are complex. I don't think that matters. So we're projecting onto a ball in a complex space. That's fine. This is all you do. And then G, the function G is going to be GDC indicator plus, no, it's going to be L1 norm. So it's going to be GCS plus GDC indicator. This should do soft thresholds on the magnitude. Ooh. These are different, so one's going to be better. Soft thresh works on complex. can always change this later. So I'm going to get rid of all the V's here. That's what I'm going to do. Okay. Mag in and mag in are the same. This looks better. This one. Unless it's a bug. What's with these scaling factors? This is wrong. Oh, mag in. No. Greater than thresh. Is equal to in mag in greater than thresh. Times mag out. Mag in greater than thresh. That changed nothing. What on earth? Oh, okay. This is probably right. This is for a weighted norm, weighted L1 norm. One minus scaling factors is mag-in minus thresh divided by mag-in. So at the threshold, you get 0. Yeah. That checks out. Okay. No bug. Just different ways to calculate it, I think. As long as we're here. Nope, not doing that. Okay. I'm not solving this. Huh. Seems MFS is dominating norm A. If use PDHD is true, use PDHD. Else if use FISTA, use FISTA. Use LSQR. We'll keep that one. Okay. I have an idea. We're not going to need CS if this idea works. The thing is that with compressed sensing, you're not dealing with the normal Gaussian noise. You want the threshold to beat down the level of the coherent noise. The incoherent noise. And that's a different value. Before I go off, let's see how much different the value is. So we're going to look at the zero filled. Any chance will be times 10 to the 5. Noise bound CS 3 times 10 to the negative 8, 10. Noise bound is 4 times 10 to the 11. And if I do this, before we change anything, this is just times 10 or so. This isn't going to fix it. What's the problem? Not enough input arguments. Didn't this just work a second ago? Here. Okay. $255. Confused. Thought we did this a second ago. Noise bound is different now. Doesn't matter. Here's the sun. Yeah. So we're 100,000 off in our noise bound. I'm gonna have to think on that one. I'm gonna take a break. Maybe we'll see you guys later today. Till then, have a great day.